In this video, we're going to find the pH of two different weak bases. To do this, we're given the information about the weak conjugate acid. For hydrogen cyanide, the Ka is 4.9 times 10 to the minus 10, and for HF, the Ka is 6.6 times 10 to the minus 4. Well, if we want to find the pH of a weak base in solution, remember that the reaction for a weak base acting as a base is that it has to steal a proton from water. So if you put just, say, sodium cyanide in the water, well, the only source of protons for that cyanide is H2O. This is going to make HCN, and it's going to make OH minus. There's some initial value. With these molarities, we'll assume it's 1 liter. 0.01 moles of cyanide, no HCN, no hydroxide yet. There's going to be a change. I'm going to lose some cyanide, I'm going to gain some HCN, I'm going to gain some hydroxide until I reach equilibrium, where I'll have 0.01 minus X, X, and X. Well, this is cyanide acting as a base, which means I need a Kb. I need an equilibrium constant for acting as a base, but I only have the Ka for the conjugate acid. Whenever we're trying to do an equilibrium calculation using the conjugate base as our starting molecule, we need to do some conversions. The Kb is going to be our base reaction here. We're going to have the HCN as a product, we're going to have the OH minus as a product, and we're going to have the Cn minus as a starting material. Water is constant, and so it factors out. But I need that Kb. How do I find Kb? Remember that your Ka times your Kb for a conjugate acid-base pair must always equal Kw. Well, my conjugate acid and base here, I've got my base, it's cyanide. I've got my acid, it's HCN. If the reverse reaction happens, HCN is going to give away that H plus to go backwards, and so it's the conjugate acid. We do know the Ka for the conjugate acid of this pair, 4.9 times 10 to the minus 10. That times Kb must equal 10 to the minus 14, Kw at 25 degrees Celsius. Divide the Ka across, and our Kb equals 2.041 times 10 to the minus 5. And so we can solve the Kb that we need to plug in to be able to finish our equilibrium calculation. Now that I have Kb, 2.041 times 10 to the minus 5 must equal our HCN concentration, which is X, our hydroxide concentration, which was X, all over our starting material, our cyanide, which was 0.01 minus X. In this case, 10 to the minus 5 versus 10 to the minus 2 for our concentration. That's far enough apart that we're not too worried about X being that large. So we can reasonably safely assume that the minus X won't significantly change our concentration. And so to save us the problem of a quadratic, we can cancel that out. Multiply this up, 2.041 times 10 to the minus 7 equals X squared. X equals 0.000452. Well, that is our hydroxide concentration. So that equals the hydroxide concentration, which means we can find the POH. It's going to be the negative log of 0.000452. Our POH, 3.345, which means our pH for this solution, which is going to be 14 minus the POH, 10.655. A solution of 0.01 molar cyanide is going to have a pH of about 10.6. Similarly, let's find this for the fluoride. Ka is 6.6 times 10 to the minus 4. 0.01 molar F minus. Ka 6.6 times 10 to the minus 4. Well, same idea is occurring here if we want to find the pH. My F minus, so I add sodium fluoride or lithium fluoride perhaps, some kind of fluoride ion without an H+. The only option is for it to react with the water. This will form HF and hydroxide. So our weak base, again, reacts as a base, and in doing so, it creates a conjugate acid. Our initial concentration of F minus was 0.01. We had none of the others. There's a change. Our starting material will get used up. We'll make products. We'll reach equilibrium. 0.01 minus X, X and X. Again, I need a Kb because we are doing the base reaction here. We have our base as our reactant, reacting with water to make conjugate acid and hydroxide. To get our Kb, well, it's going to be Kw, 10 to the minus 14, divided by Ka, 6.6 times 10 to the minus 4. Our Kb is going to be 1.515 times 10 to the minus 11. So I can set up my equilibrium expression. My Kb is going to equal my products, HF and hydroxide, over F minus. 1.515 times 10 to the minus 11 is going to equal X for my HF, X for my OH minus, and 0.01 minus X for my F minus. Kb is really small, so likely minus X isn't going to significantly change our value, so we can remove it to simplify so we don't need the quadratic. 1.515 times 10 to the minus 13 will equal X squared. X will equal 3.893 times 10 to the minus 7. That is our OH minus concentration, since we are following the base reaction, which means I can convert this to POH. Negative log of 3.893 times 10 to the minus 7 is 6.409. pH equals 14 minus POH. The pH of our F minus solution, 7.59. It's just a little bit basic. Pure water is 7.01 molar F minus is 7.6. That added just the tiniest bit of hydroxide versus neutral water. F minus is a pretty bad base. It's not very good at picking up that proton. It really doesn't want to do it. And so very, very little occurs and barely alters our pH from neutral water.